Right, okay. So we continue with our coding for solving this problem. Okay, so for solving this example for study Stokes flow. Okay, so we have a unit domain and we have a wall boundary here. So on the left, bottom and right, at the top we have a lid. So where we have a specified value for the horizontal velocity. Okay, so to start with, so we use our Gmesh. Okay, so I have the domain, and at this point you should be able to create the domain and then mesh it. Okay, so I am creating a 10 by 10 mesh with 4 noded elements. This is a very structured mesh, right? Okay, so we generate the mesh, we export it. Okay, and then we have all the information about the nodes or element and the boundaries and so on, right? Okay, so for the boundaries, what I have, so I have two flats, two tabs, one in the wall. Okay, so for the wall, okay, so we need the left boundary, bottom one, and the right boundary. And for the wall, okay, we need the top one. Okay, so two boundaries and then the whole domain. Okay, and then yeah, so mesh it, export it, save a file. Okay, now I'm going to show you the main file, like MATLAB Octave code for solving this problem. Okay, using the stiffness function subroutine that we have that I have shown you earlier. Okay, in the previous part. Okay, so we start with the we close everything, we clear everything. Okay, and this is the mesh file. Okay, LDC lid driven cavity 2D Q1 is 4 noded element and 10 by 10 mesh. Okay, and our material parameters, mu viscosity of 1, and there is no body force in this problem, so 0 0. Remember here in this case the body force should be a vector of size 2 by 1. Okay, and we are in a 2D problem, so NDIM number of dimensions is 2 and NDY of number of degrees of freedom. Okay, so number of velocity degrees of freedom at each node. Okay, and then we extract some information from the mesh file from the mesh. Okay, so once we read this file, we get this variable or object mesh. Okay, so we get number of nodes in the mesh, number of elements in the mesh. Okay, yeah, in the mesh. Okay, and since we are using the 4 noded element, we call this is called Q1. So we are using the same basis function for both velocity and pressure. So we denote it like this Q1 Q1. Okay, and so number of nodes per element for velocity is 4, and it is the same for pressure. Number of nodes per element for pressure is 4. Okay, so now we can calculate the total number of velocity degrees of freedom for this problem. We know the number of nodes and we know the degrees of freedom at each node, the velocity degrees of freedom. So the total velocity degrees of freedom is stored in this variable, and then we are using the same element for pressure. So the number of pressure nodes for the problem is equal to the number of nodes in the mesh, right? Okay, we are using the same mesh for velocity and pressure. So, and pressure is a scalar, so the number of pressure degrees of freedom is equal to the total number of nodes. Since velocity is a vector and in 2 dimensions it has 2 components, so the number of velocity DOF is 2 times the number of nodes. If we are in 3D, then we will do it like 3 times the number of nodes. Okay, and then the total number of degrees of freedom. Okay. Okay. or we can just separate number of velocity DOFs in the problem. Okay, number of pressure DOFs in the problem. Okay, and total DOFs. Okay, so then we need some arrays to store the information for assembling. Okay, so first we create element node connectivity array. So this is a duplication, but it is okay. So what we are doing, so we are extracting all the information from this message, like the mesh object, for all the quad elements. We are extracting all the nodes of each element. So this is our, so this stores element to node connectivity for each element. And for assembling, we need, okay, so for assembling, we need to know to which rows and columns the four blocks of the element stiffness matrices, right? So they should go into the global stiffness matrix. Okay. So for KUU for each element, so all those entries should go into the which rows and columns in the global matrix. Okay. Now, so what we need we need total 4 different arrays. Okay, so 2 arrays should be enough. Okay, so we need 2 different arrays. So one array for the rows of U, one array for the rows of P. Okay, since the matrix is symmetric. Okay, so we use the same for columns of U and columns of P. So we need one array for the rows of U and one array for the rows of P. Since we are using the same mesh for P, we can get the element node connectivity for P. But for U, since velocity has 2 degrees of freedom, we need to calculate it differently. Okay. So we need element DOF connectivity matrix or array for velocity and element DOF connectivity for pressure. Okay. So these arrays should be of size n element. It should have an n element, like all the rows for all the elements, and the columns are different. Okay. So what this means is, okay, so let me quickly run this, and okay, so we'll look at it later. Okay, so in the element node connectivity, okay, so I'm going to print this. Okay, so let's take the first for the first element. Okay, so these are the nodes for the first element. Now to calculate velocity degrees of freedom, what we need, so at node 1 we store it like 1 and 2. Okay, so x1 is x velocity, y2 is y velocity. At node 5, 9 is x velocity, 10 is y velocity. At 41, 81 is x velocity, 82 is y velocity. At 40, 79 is x velocity and 80 is y velocity. So we need to create this array. So to create this array, so what we do, okay, so we have defined this array with all zeros, and then we populate it. Okay, so for all the elements, okay, so for all the rows, the columns starting from the first column and okay, and the straight of 2, okay, every second column. Okay, starting from the first column, every second column, that is 1, 3, 5, 7 will be filled with this. Okay, so element connectivity, that is the node connectivity, element node connectivity minus 1 multiplied by 2 plus 1. Okay, this gives us all the x degrees of freedom, and this gives us all the y degrees of freedom. So y degrees of freedom we put in the even columns like 2, 4, 6, 8. Okay, so with these two rows, with these two lines, 79, sorry, 37, 38, we get the x and y degrees of freedom for each element. Okay, so if you look at this, okay, so that's what we said, right? So 1, 2 for node 5, 10, 9, 10, for node 41, 81, 82, for node 40, 79, 80. Okay, so this array gives us all the degrees of freedom for each element. So we can extract this each row for each element and then use it for assembling. Okay, so for pressure, it is straightforward. So, okay, so it is scalar. So whatever the element node connectivity we have, we use it for the pressure. Okay, after defining the arrays, we process the boundary information. So since we have boundary conditions everywhere on the domain, so we extract all the boundary nodes. Okay, so we extract all the boundary nodes from the line, from this line variable of the mesh object. Okay, and then we flatten it, that is create a 1D array, and then we find the unit values. So at this point, so we should have all the boundary nodes, and since both x and y velocities are specified on all the boundary nodes, we need to again do the same as this. Okay, so we need to calculate the degrees of freedom, that is x and y velocity degrees of freedom at all these boundary nodes. Okay, so that is what we are doing. So for boundary nodes, this is the x degree of freedoms, these are the x degrees of freedom, and these are the y degrees of freedom. Okay, I'm simply sorting. Okay, and yeah, so sorting them. Okay, and then we flatten it. So at the end, we need a one dimensional array, so that we can use for different purposes. Okay, so at this point, we have all the degrees of freedom for all the fixed degrees of freedom for velocity. Okay, so these are all the degrees of freedom. Okay, so up to 80. These are all the velocity degrees of freedom. Okay, that are fixed, that are specified. They can be 0 or they can be non-zero. That we will see later. Okay, and for this problem, okay, so for this problem, so for any problem, okay, so if we have pure velocity on all the boundaries, okay, so then the pressure is determined up to a constant. Okay, so what we do is we fix the pressure at this corner at 0 to that constant 0. Okay, so that means we specify 1 degree of freedom for pressure. Okay, so we specify the first pressure degree of freedom, and that would be 1 plus velocity degrees of freedom. Okay, so be very careful here. So I'm going, okay, so for in the global system, okay, so we have u and p. Like I said, first we store all the degrees of freedom corresponding to velocity, and then we store all the degrees of freedom corresponding to pressure. This is the same as what we do at the element level. Okay, so at the global level, okay, if we assume that there are m velocity nodes, okay, m nodes in the mesh, then we have 2m degrees of velocity degrees of freedom in 2D. So first we store all the 2m values. Okay, so 1h, 1h, 1y, 2h, 2y, mh. Okay, so this is mh. Okay, mh, my. So we store all the 2m velocity degrees of freedom first, and then store the pressure degrees of freedom. So to fix the first pressure degree of freedom, what we need? So 2m plus 1. Okay, so that is what I have here. So this is the first pressure degree of freedom, and we are appending it to our DYF fixed DYF vector. Okay, so that is what you see here, 243. Okay, so we have a 10 by 10 mesh. So that means we get 11 by 11 nodes. So 11 by 11 is 121. And so we have a total of 121 nodes. Okay, and at each node we have 2 degrees of freedom. So 242 velocity degrees of freedom. And then the first pressure degree of freedom would be 242 plus 1. So 243. Okay. Then once we know this array of all the fixed degree of freedom, we can calculate the array of all the free degrees of freedom, okay, for solving the system. Okay. Okay. So now we have prepared all our like arrays and for bootstrapping for assembling. Okay. Next, we are going to initialize our solution vector. Okay. So this is our solution vector, and we initialize another vector, another array, solution specified, where we store the specified values at the boundaries. Okay. So here we have 4 boundaries and we have 2 tags. Okay. So in the first tag we have the left, bottom and right representing the wall. On the wall both the velocity values are 0. So we don't need to do anything for the elements or nodes on the tag 1 with the tag 1. But for tag 2, that is for the lead, we need to specify this velocity. Okay, like I said, so the x velocity should be 1, but to smoothen the profile we use this profile. To smoothen the velocity profile we use this expression with a very high value of a. Okay, so what we do, we loop over all the so all the elements, 2D elements on this boundary, and for each node we calculate the h velocity based on the coordinates. Okay, so we loop over all the lines, that is boundary edges, and if the tag matches 2, that is for the wall, then for each, okay, so we get all the nodes in that. Okay, so that means let's say, so let's take this first element. Okay, so for this element we have 2 nodes. Okay, so we loop over all those 2 nodes. We loop over all those 2 nodes, and then for each node we get the node number, and then from once we know the node number, we can calculate the x degree of freedom, and then for this node, what are the x and y coordinates? We can get it from the this pose variable in the mesh object. Okay, we take a value of a as 100. Okay, so in this expression we take a value of a as 100, and then so this at this degree of freedom, okay, we like populate the solution specified array with this expression. Okay, so we do some duplicate calculations because when we loop over this second boundary element, so we are looping over this node again, but it just replaces the value, so there is no harm. Okay, so we can do it other way as well. So we can extract all the nodes on this top boundary and then loop over all the nodes. So that also we can do, but it doesn't matter. It doesn't change much. Okay, so now we have the boundary velocities. Okay, so next what we can do, we can calculate our global stiffness matrix, global force vector. Okay, so first I am initializing them to zeros, then loop over all the elements. So then we call our element stiffness matrix force vector the function for steady states, and we get all this like 6 variables. Okay, so we assemble them into the global global stiffness matrix and global force vector. Okay, so what I'm doing, so we already have this prepared element dy of connectivity array for velocity. So for each element we get all the columns. So this is the indices for assembly for, let's say, like 1 is velocity and indices for assembly 2 is pressure. Okay, so these are the velocity degrees of freedom for the for the element, and these are the pressure degrees of freedom for this element. Now, not be very careful here again. So we have the element DOF's conductivity for pressure, but they start from 1. However, when we assemble, we are assembling after all the velocity degrees of freedom here. Okay, so here this rho is velocity DOF plus whatever pressure DOF we have here. Okay, so we can do this either here. Okay, so we can do this here or later. Okay, so we can also do, like we could also do this here if you want. Okay, but if you do this, the only reason I don't do it here is it will be difficult to debug in case some things go wrong. Okay, so that is why it's a good practice to add this offset. Okay, so like offsetting the u degrees of freedom. Sorry, we offsetting the p degrees of freedom. P degrees of freedom. Okay, so we are offsetting the p degrees of freedom. Okay, with the velocity wave array. And then like assembly is the same. Okay, so for KUU we use the dwaves for velocity. For FU we use the dwaves for velocity. Okay, and then for KUP it is a like off diagonal. So 1 and 2 we use like this is for velocity, this is for U, this is for P, and for PU P and U, and for PP P and P. Okay. And then we also have FP. So in this case it is 0, but we still assemble it for future. Okay. Okay. So once we complete the loop, we have the global stiffness matrix and force vector. So that is we have this full global stiffness matrix. Okay, and the full global force vector. Okay. Afterwards, we loop over all our fixed DOF. Okay, so we calculate the contribution to the right hand side, and then what we do, we also store the specified degrees of freedom value at the corresponding location in the solution vector. Okay, so that we have only one variable with all the information. Okay, so and then the solution procedure is the same. Okay, so after this one step on line 122, we have the solution and then we plot it. Okay, so I'm going to run this. Okay, so this is our pressure solution. Okay, now if we compare, okay, so we have a steep value here and steep value here, but if you look at the scale, it is minus 10 power 17 to plus 10 power 17. Okay, and if you notice here, there are like oscillations. Okay, so one value is up, the next value is down, and then the following value is up. So like these are like this is a like checkerboard pattern, like up and down, up and down. Okay, like we can see here. Okay, so this is up, this is down. Okay, so like that. And now before we like I discuss the solution, okay, let's go back to the code. Okay, now so we have the global stiffness matrix. Okay, so let's so this SPY function helps us to see where non-zero values are in the stiffness matrix. Okay, so these are all the dots where the values of the stiffness matrix are non-zeros. Okay, so we can clearly identify it. Okay, so this is our KUU matrix, this is our KUP matrix, and this is our KPU matrix, and KPP is 0, so that is why we don't have any entries here. Okay, Now that's about the code. So the major differences are that since we have more degrees of freedom and more variables, the bootstrapping becomes little bit difficult. But once you follow logical steps, you can easily like understand how to code this. Okay, now coming back to the solution. Okay, so this is our solution and there are oscillations. Okay, so the reason for the oscillations I'm going to explain in the next part.